Okay. Uh, Welcome everyone to the fourth technical session of MSFP. This session we have a couple of work on some applications to some specific domain areas. So our first talk by Artems will be on an application of polynomial functors or containers to array programming. So go ahead, Artem.
All right, thanks. As you correctly said, so this is going to be my journey through trying to formalize arrays in independent type contexts using containers, discovering a new container operation that seemingly is unknown to people and in literature, discovering that using this operation you can have an interesting array hierarchy of types, and basically looking at practical application of this thing. So when I say formalizing arrays, what I mean is this. So I'm aiming for, well, first of all, rank polymorphism. That the bread and butter of array programming. So the ability to be able to define functions that operate on arrays of any rank and shape, right? Then I also insist on checking bounds statically, so that indexing errors, out of bound indexing is impossible at runtime. And I want to be able to represent any operator from the APL programming language, because that's, well, the essence of the array programming, right? And extensibility is nice, but that's optional. So it is important to mention that if we seriously take these conditions these criteria that I've described, then we inevitably have to use dependent types, because, well, if you want to statically track the shapes of the arrays, it's the easiest way to do it is in the type. And if you want to support operations like take and drop or many other APL operators, then inevitably you'll find yourself in a situation that the shape of the result of the operation depends on the value of the argument. Therefore, dependent type is essential here. And here's the first approach that basically fits all the criteria. That's a pre-container approach that I started from. So basically what we do here is we model the array as a function from some index space to values, and arrays keep the elements of type X. And here's a function that models, well, that gives a value to the array. And just to be sure, we're talking about hyperrectangular, homogeneous, multidimensional arrays. So it means that the shape of the array is fully defined by a vector of natural numbers, which basically explains the length of every axis in d dimensions, right? And then what is the indexing? What is the index space of a given shape? Well, the index space of a given shape is basically also a tuple of natural numbers where each element is bound by the corresponding element of the shape. So the index must be component-wise less than all the elements of the shape. But it's important to mention that's going to appear later, that the structure of the shape and the structure of the index always match in this model. Okay. So using this thing, basically you can do a lot of things. And for simple cases, like you see on this screen, you don't even have to provide many proofs, right? So if from the way the types are constructed, when you write, for example, operations on matrices like transpose or matrix multiply, as you get down to the individual index components, and you carefully reshuffle them around, then the type checker it can see that basically all the indexing is correct, and you don't have have to do any kind of actually proofs. If you really work on rank polymorphic operators, then surely you might find yourself defining some properties. But in simple cases, it works out very nicely and automatically. And then how do we get here from here to containerization? First, let's remind ourselves a bit what containers are. It is a lot of things, but for the purpose of this work, for this paper and for this talk, as the name suggests, really, it's a collection of indexed things, right? And in order to define a container, you have to choose a type for the shape, and you have to choose a position, which is a shape-indexed family of types, right? And then the interpretation of a container, so basically the operation that gives you access to the actual elements, is given by this function. So to interpret container with element type X, it means that we just create a dependent pair where the first element is the shape and the second element is a function from the positions of that shape to X. Okay. So in that sense, for example, list is an instance of a container. So list is defined by a container nat fin. And if you expand the interpretation, then you'll see that basically it says that, well, list can be modeled by a dependent pair where the shape is a natural number, so just the length of the list, and then the positions are functions from fin n to X. So really, the nice point for me is that containers give you the most they never talk about the way your data structure is organized, right? So you just have an interface in the form of a function, and the function says, well, okay, you have indexable thing, and I'm not going to explain what is the internal structure. So if you think about the compiler, it means that, well, from this representation, you can implement your actual data storage in any which way you like. You know, the interface doesn't care. Okay, so array is obviously a container, and let me explain how would it look like in the containerized representation. So first, let's recall that vector can be modeled by the function fin n to X, right? That was just on the previous screen, and the indexing can be modeled like this. So it is also a vector of d elements, but where each element is fin of the corresponding shape component, right? And in that case, array is just a type constructor that takes the rank, the shape, and a function from indices to values. Okay, so that's what we start from. Then we can uncurry first two arguments and notice that this function here looks suspiciously like a function here, right? So we can rewrite already the array type as an interpretation of the container, where the first element is going to be a sigma, well, the vector, in essence, the vector of natural numbers, and the second one is going to be the positions are going to be the IX type written with fins. Then we can notice that the sigma is also a container itself, right? So as I was showing on the slide before, and from looking further at this, we can notice that this operation suspiciously looks like a result of some operation on the containers, right? And then we try to think carefully about how the general operation on the containers could look like in order to produce such a result, and we came up with this formulation, right? So we call this diamond. For it, I'm not sure why. Well, is it a good name or not? Doesn't mean much. So what we do in order to compute the result of two containers, we say, okay, so we interpret the first container with the shape of the second container, and then the positions of this operation are going to be given by a product of these, right? And then we have b many d's, right? So we're creating a dependent function that basically puts these together. And in that case, the array can be rewritten as a NatFin diamond NatFin interpreted with x. And somehow, if you think about rectangular arrays, some sort of vector of vectors thing is happening there. So that is reassuring. Then the operation itself in isolation turns out to be rather interesting. Well, first of all, it looks like a weird operation. It's not associative. It's not functorial on both arguments. It's only functorial on the right. People never tried this operation before, and it's not clear what exactly it's doing. And I think the satisfying explanation on what it may be doing is is by looking at its relation to an operation on container that is known as a tensor product. And the tensor product is defined rather straightforwardly. So you take, if you want to compute a tensor product of two containers, then you pair up the shapes, and the positions are also paired up. And if you think about a classical tensor product, then really that's exactly what is happening, right? So you conceptually you choose you choose the shape of both containers up front, so this A pair AC, and then at every position of the container AB you insert the containers DC where C has been chosen beforehand. So it's kind of this homogeneous nesting of things. And then the next question you might ask, what happens if you want to compute an n-fold tensor product of container CD? And how do you even define this operation? Well, how do you give the boundaries to this tensor product? Well, you can surely choose to give a natural number and then recursively unfold the multiplication, but you can also choose to set the boundaries of this tensor product by using yet another container, and that's really what is happening in this diamond operation. So basically, we choose a container AB, and then we say, okay, just plug the container CD without interpreting it at all the positions of AB, right? So just plug the container CD and then fold the tensor product, right? So really, one way of understanding this diamond operation is it's a generalized tensor product where the left-hand side is this counting container or boundary container. And yeah, the funny analogy that one can observe with this diamond operation, that it has a similar behavior to tensor product when we compare to container product. So in the container product, you compute also you pair the shapes, but the positions are so you compute a coproduct of the positions. But if you go to tensor product, then you replace this plus by times, right? And then this diamond operation does a very similar thing to the container composition. So in a way, you replace a sigma with a pi, which, again, if you think about it for some time, then it kind of makes sense. I mean, there's this tensor tensor nature of this diamond operation. Now, the interesting thing about this diamond is that as it's closed on containers, you can iterate it, and you can iterate it in two different ways. You can associate. Well, you can define this operation to be associative on the left and on the right. And you can start with a unit container, so it's a container of one shape and one position. And then, well, you can iterate. You can keep multiplying on the left or on the right. And as the operation itself is not associative, you're going to get different results. And it is instructional to look at the third application of, well, either AL or AR. And what happens here is that if we are right associative, then by multiplying kind of on the left side, keeping multiplying on the left, we enrich the structure of this boundary container. So the boundary container turns into inhomogeneously nested n-dimensional array. So in the third instance, it is a two-dimensional. In the fourth instance, it's going to be three-dimensional, and so forth. So it's a vector of vectors as many times as you multiply this, and the rest is the same. So the indices are going to be have exactly the same form as here, but they're going to be bound by corresponding elements. Right? So you can create arrays of these weird shapes. And if you choose to make this operation left associative, then what happens is that the array of level n becomes the shape of the array of level n plus 1, and that's easier at least to understand this from this table. So we start with level 0, which is which shape is just a unit, and well, in positions, the arrays at level 0 are just zero-dimensional array, typically called scalars in the array theories, and they only store one element always. Then level 1 arrays are they have shape level 0 of natural numbers, so just one natural numbers, and well, they keep so many x's, right? So they keep a vector of elements. These are just vectors, right? Level 2 arrays, as the multidimensional arrays as we know them, their shape is characterized by level 1 arrays. So the vector of natural numbers, and then you can carry on. So for example, level 3 arrays are arrays which shape is characterized by the multidimensional arrays. So the shape itself and the index, the corresponding index into such an array is going to be multidimensional. So all we do here is we enrich the structure of shapes and indices. Now, it is important to mention that here we're not creating a conceptually new data structure, because everything above level 1, all the arrays of level higher than 1 can be mapped into vectors, right? But that's already a well-known thing. So I mean, if you have a container of finite number of elements, and you can order your indices, then well, you can surely linearize the content of your container into a sequence. So then the question is, well, okay, but if it is the case, then why do we want to have multidimensional arrays at all, yet these crazy multi-dimensional arrays? And to answer this, let me give you a brief demo. So I mean, this is the hierarchy that I'm actually interested in, and I'm going to show you why this enriching of the shape may be of a practical interest. So I'm going to switch to the APL session. So and I'm going to walk you quickly through the following problem. So look, I have an array A, right? So this is an array is of shape 2 by 6, right? So it's a two-dimensional array. It has 2 rows, 6 elements in each row. And what I want to do, so I want to apply a function. So I have a function sum. Basically, sums all the elements in the array, and I want to apply a function sum to the tiles of the array A. So I want to tile the array A into 2 by 2 pieces, right? And apply sum to each piece, and basically get back 3 elements. So when I say tiling, so I mean 0, 1, 6, 7, 2, 3, 8, 9, and so forth. Now, the point is that currently there is no single operator that's doing this. I mean, you can surely write a small expression that's going to compute this, but not with a single operator. So, but let me tell the other part of the story. So, okay, let's assume that we could have tiled this. Then we would end up with an array of a shape 1, 3, 2, 2. Oops. That would look something like this. So you see, if I plainly reshape the array A, it does the tiling incorrectly, because it tiles the array from the flattening, and we need to tile it a bit in a smarter way. But okay, what this tiling is good for? This tiling is good for because there's a very frequent operator in APL that is called the ranked operator. Looks like this, and what it does, it allows me to say, okay, I have my function, and then I can pass an argument to the ranked operator and apply it to well, let me do it like this. So I can pass an argument, and I can apply it to this array. Okay. So what it just said is that, look, I pass the argument 2 here, and it says that it is going to apply a function to the elements that you find in the last 2 dimensions, right? So in a way, it's something like a generalized map. But if you're dealing with lists of vectors, then, well, I mean, you can only map in a certain, well, in one way, because your element type is fixed and you don't have any dimensions there. But if you're dealing with homogeneously nested vector, then in principle you can decide, and your operation is rank polymorphic, so sum is rank polymorphic, so I can apply sum. Oops, I can apply sum to, I don't know, 5, right? So it works perfectly fine. Then I can decide which elements I'm going to feed to my function, right? And in that case, and in this case, what it does, it actually, this ranked operator says, okay, I can cut my shape vector into the outer part and inner part, and apply, well, and map my function on the outer part, right? Okay, but coming back to this hierarchy. So why is it useful? And I think the core, the important answer here is this. The arrays, in principle, yes, they are views of a sequence. But why would you ever want to create a view if a sequence is kind of works fine? And I think the answer here is that you want to create a view because you want to attach a certain proximity matrix to your elements, right? In a sequence, each element has only up to 2 neighbors, right? In the multidimensional array, the number of neighbors go up, and you can talk about much more interesting distance relations between the elements. The same thing happens here. So look, if we want to preserve the operations via reshaping, we'd reshape it like this, and then we're almost there, and then we'd need to map over these dimensions, right? But these dimensions are spreads; they're not neighbors. So there's no way to apply this ranked operator. However, if we would assume that our shape were a bit richer than just a vector, then we could consider the shape like this, right? And in that case, we can do something with this operator. For example, we can take a column, we can rotate the matrix, right? So we can bring all the operators that we use on normal arrays in the position of the shape, and remap one shape into another in such a way that the effect on the array elements can be trivially computed. So if you can map one shape into another, you can always reshuffle the elements of the array accordingly, right? And that's exactly what I'm doing in the paper. So I have an Agda formalization. I don't have time to go into the details, but please have a look, where I extend this idea of the ranked operator and make it level polymorphic. So what I'm saying is that, well, it doesn't really matter how rich your shape is. All you have to do is you have to define a way. So you have to define me a hyperplane that cuts the shape into two parts, right? And if you do it, and if it's actually a hyperplane, then these two parts can be turned into, well, then the array of the shape that is cut into two parts can be turned into a nested array, and then you can do the map on the outer level and feed the inner array tiles into the function, right? So I describe this idea very precisely in Agda, and I show how it's done. But the overall intuition behind this is exactly that, right? So by putting richer structure into array shapes, we can use all the huge amounts of operations that we have already on the arrays. Okay. And okay, I'm going to skip this. I'm going to just go to the conclusions. So what happened here? So I mean, I tried to use containers to formulate multi-dimensional arrays, and I discovered an interesting operation. And I think there's still plenty of things to study about this operation. And I discovered this interesting hierarchy that seemingly that is very natural at two levels, because, for example, in APL everything is an array, right? And therefore it is nice that this hierarchy mimics exactly that. So you can do all the operations that you do on shapes and on scalars as you can do on arrays. So I formalized this in Agda. There were a few problems that I described in the paper. I've implemented key array operations, reshaped, flattened, ranked, and so forth. And I worked out the example. So the ranked, this ranked operation is the hardest one. It's all available at GitHub. And I'd like to say big thanks to Peter Hancock, who should have been an author of this paper, but he preferred to, play harmonica or something instead of paper writing. And Bodo Schultz, who we spent a productive few days on discussing this multi-dimensional arrays and bending our minds over it. Yeah, I think that's it.
Okay, thank you, Artem. Clap, clap, clap. Okay, so we're a little over, so I think we only have time for maybe one question, but this was asked by both Manuel Barons and Wouter Seerstra. in the chat was essentially, do you have an explanation for how to understand this diamond operator as an operation on the functors induced by the containers, like directly working in the semantics?
I'll have to think about this. So I think the explanation that I provided works the best for me because it captures a lot of intuition. But for functors, as I said, it is operation with weird properties. So I'm not sure that if there is an explanation, that it's not a trivial one. So there's something funky happening there. So understanding it via this tensor product seemingly is the easiest way, but I might be wrong.
Okay. Well, there's several more questions on the Zulip, so let's continue the conversation there.
Right, sure.
Let's see. So yeah, you stop presenting, and then Mick will start. Okay. So our next talk will be by Mikkel here, and on applications of module theory to databases. Take it away.
Thank you. So let me start with a little teaser. So a triangle query is it's a query where we try to find 3 points in a graph that are all connected like a tree cycle. And as an example, let's take the Wikipedia database, and let's say there's a link between A and B if A has a reference to B, like a link. And then let's try to execute this query in MySQL. And let's suppose that we have sort of done a reasonable job of optimizing the query, and we've made our indices and so on. How long does it take? For this particular example, it takes almost 2 hours to get an answer. Now, what happens if we code up a Haskell function using some fancy algebra, but otherwise just a 3-liner, basically? It takes about 10 minutes to write. It takes about 4 seconds to execute. So how is this simple Haskell function? It's clearly asymptotically better than the MySQL execution. And it's clearly a lot simpler. So how does this happen? Well, the general strategy that we're using in this approach is, well, take something like query processing and then forget all we learned in the freshman course. Like forget relational algebra, forget SQL. Let's use algebra instead. Let's use module theory, linear algebra, that kind of stuff. Then we take a dose of category theory and sprinkle on top, and then, a few days later we get results. We can recover previous results like factorized databases, and we can generate new results like efficient algorithms for query evaluation. We can get efficient data representations beyond what has been seen already. And so that's the general approach that we've been using in this work to try to combine sort of algebra with query processing. Okay, so let's get some basics out of the way. Module is it's basically an abelian group and a ring, and the ring is acting on the group. So we have set, and we have addition of elements, and we have scalar multiplication. And then they obey all the laws that you would want it to obey, including commutativity, which is important. And then given this algebraic structure, we can of course have maps that preserve the structure, which in this case is linear maps, or homomorphisms. And Additionally, we want to consider the idea of bilinear maps, which is just, well, what if we have two different modules, well, a pair of modules, and we want to map out of them? Well, then we want something that is linear in each argument separately, and that's what we're going to call a bilinear map. And this the structure of modules and linear maps forms a category, should be well known. And so let's look at the inhabitants of this category. We have the trivial module, sometimes just called the zero module, consists of a single element, just a zero. There is the ring itself, here called K because we're sort of thinking a bit about linear algebra, so K is a field sometimes, but in general it can be any ring. So that forms a module, and then for any two modules we can form the module consisting of linear maps with pointwise operations. Okay, so with the formalities out of the way, let's look at some of the more interesting constructions. The first one of which is coproducts. So the coproduct, well, so the general property works like this, which should be familiar, that we have some family of injections, and then for any other module with a family of injections, we have a unique map out of the coproduct, which would denote with case because it's essentially case analysis. And well, the thing is, in the category of modules, coproducts and products kind of coincide in the finite case, but we're not going to talk much about products here. But the coproduct it's not quite, if you're used to thinking about coproducts in the set theory or the category of sets or types, it's a little bit different here because of the additive structure. But we'll get to that. And then the particular case of with arity 2, well, that's just a binary coproduct, which we call a direct sum. So we have this kind of handy notation for just adding two things of different types. Now here's where it gets interesting. So if we look at this in the most abstract setting, which is just a category with, the category of modules, but it can be even more general than that, but let's just look at modules. We can prove the following natural isomorphisms. That if we have the coproduct of the empty set, well, that's the trivial module, and the coproduct of the unit set is just the ring. And then sums of sets become direct sums of modules, and product of sets become iterated modules. So with this, we actually have a representation for all polynomials of sets, right? So and we can do, I haven't shown this here, but we can do fixed points as well. So essentially, we can take any algebraic data type and then generate a coproduct over that, and via these natural isomorphisms, we can decompose it into iterations, direct sums, and the primitives here. And what this turns out to be is actually the structure of generic tries, as in the thing that you code up in Haskell using type classes and associated data families and that kind of stuff. This is the exact same thing that we get just by looking at category theory and natural isomorphisms. Right, so let's look at a particular case of a coproduct, a very useful case. So let's just, for convenience, fix the ring to be integers. And then let's look at a coproduct, which is just a bunch of copies of the integers. So it's just a homogeneous coproduct with b copies of the integers. And then the specialized property looks like this. So we can map out of this module just by specifying what happens to each element. And this we're going to call polysets. So it's the functor here that takes a set into a module, and we call that the polyset over that given set. So what does this mean in practical terms? Well, so the elements of polysets are finite sets. So we have a polyset consists of a finite number of elements, each with a multiplicity. This is how you would denote that in like existing multiset developments. But using annotation, well, that's just the linear combination. So we're using the introduction rule for each element to make it into an element of the module, and then we just multiply, right? So it's just we're just using the notation of a module to construct elements. So we don't necessarily need to write it in this canonical form. We can just use any kind of expression in the language of modules to write down elements, but this one in particular would be like the standard canonical choice. And well, to map out, we can just, like as we usually do in the algebra, we just f is defined by its action on each of the basis elements. So the other important concept that we're going to look at is tensor products. So we can present this as a universal property as well. So the tensor product is equipped with a bilinear operator. So this is a bilinear operation from U cross V into U tensor V. And then the property is that, well, given any bilinear map, we can mediate between them by this operation, which I call uncurry. So basically it means that any bilinear map can be represented as a map out of the tensor product like this. So we don't really need to consider bilinear maps as such when we have the tensor product. We can just consider linear maps out of the tensor product. But given this tensor product construction, we have a very powerful notation, which is that, well, we can just take any element, an element from U and an element from V, and then we can just combine them using this tensor product notation. Now, this might not seem like much, but the thing is that these elements in themselves can be any kind of expression. So we can take a big sum of a number of elements, and both of them can be complicated sums, and then we just tensor them together using this tensor constructor. Now, the important thing is that we don't multiply out. So the tensor product comes with a bunch of properties like linearity in both arguments. So we could choose to say, well, let's normalize this and multiply out the sums, but that incurs a quadratic blow-up in the worst case. So we're not going to do that. We're specifically going to delay this kind of canonicalization of the tensor product for as long as possible. In particular, if at some point we map out of the tensor product, well, then we can just apply the function to each argument separately. And if we didn't map out in the first case, well, we're never going to, supposing that this function that's mapping out doesn't really care. Now, remember the tensor products are not quite the products that are not like Cartesian products in the sense that you can't just write a projection in general. Like there's no non-zero natural map that goes from U tensor V to U, because then you're throwing away information from V. There's a multiplicity in V that we're forgetting. But if the thing that we're throwing away is, for instance, a polyset, then it is possible because polysets can be counted, right? We can say, like, what is, well, in terms of linear algebra, we would say, well, it has a basis, right? But we don't really think in terms of basis. We just think, well, this is the polyset generated by this set, and therefore we can forget it in an ordered sort of coherent way, right? And then, well, we have functorial actions. We can just take the tensor product of two functions and, well, acts on them separately. Okay, so with all that, you might be wondering, well, how exactly does this connect with query processing? It was just a bunch of module theory. Well, here's the thing. Union is just plus, right? So we're dealing with polyset semantics, so we can just add things together, and that's the union. Difference, that's just negation, right? So we can just, well, it's a module, so we can just negate elements, and that's, if we want to remove something, we just take the negative and add that. And well, okay, we might go into the negative, but we can do normalization if we really want to. We don't have to do it all the time. Like in the relational algebra semantics, you're essentially doing normalization at every step, right? So you never go negative. You have to always make sure that there's no negative multiplicity. But in the multiset, polyset version, we can go temporarily into the negative, but that's not a problem. And we can insert normalizations if we want, and we cannot do it depending on like what's needed and what's efficient. So products is bilinear because we're using tensor products to represent products. Like if we have a record of several different attributes, then we would use a tensor product to combine them. And this is also the structure that we're using for computing joins. And then a lot of aggregation is actually linear. Like if we want to compute sums, we can basically just project out data that we don't care about, and then we end up with a scalar, and that is the count. Well, that is the sum. We can do counts, we can do filtering, and so on, various operations. If we want to do things like max and min, then that is possible too, but we have to then work with semi-modules and semi-rings. But the entire theory works quite fine in that case as well. Then that just means you can remove elements, but sort of negation is orthogonal to the rest of the theory, so we can sort of add it or remove it as needed to do what we want. Right, so let's look at joins. Right, so what is, I guess I should have written the type of a join, but essentially we have two polysets and then like a tensor product of polysets, and then we want to produce another polyset. So think about it this way: we have a polyset of B's. So that's like the record data that we have, probably a number of components of different types, and then we have some F which picks out the attributes that we're interested in. So A is some kind of, it might be a single attribute, or it might be a product of attributes. Like if we're joining on, like in traditional SQL, if we're joining on multiple fields, then in this case, A would be some kind of compound type. But F picks out the key that we're joining on. And so this index function, it takes the polyset and then it produces a coproduct over that polyset. So basically, we can think of coproducts as indexed modules, in this case in an indexed table. And this works beautifully with the interpretation of coproducts as tries and these representation theorems that we get from the natural isomorphisms. So basically, we think of coproducts in this case as just indices via efficient trie representations. And this is kind of a specification of what it looks like, which is just injection. Right, and then on the other hand, if we have an index, we can flatten. So we could just say, forget that we have an index, and then this works for any module, by the way, not just polysets, but we're going to use it in the case of polysets. We just throw away, like case analysis, and forget the index of this I should be an A. And then here is the interesting one. So given two such indexed modules, indexed by the same attributes, we can do a merge, and then what we get is the intersection. Right, so this element is going to consist of the intersection of the attributes in the elements of the input, and then as for values, we combine them, so we get a product of the values like this. So all in all, this can be combined into a join function. So I write the join as a join of two functions, because like that's the data we need. Like that's F and G picks out the attributes that we're actually computing on. So, I mean, it is a join of the two tables. It's just that the functions sort of carry that information implicitly, right? And it simply happens by indexing using each function and then merging them together, and then finally flattening. Of course, I mean, so the flattening is done because that's how join works. Like we want a table back as a result, but if this is part of a larger query that we're processing, then we might not want to flatten immediately. We might want to keep the index for later, and that's actually going to be important for more complicated joins. Right, so how does this merge function look like? Well, so the thing is, it works on coproducts, and coproducts have coproducts kind of work differently for each type, or rather, we can analyze this index type of the coproduct to determine what it looks like, right? So remember that we have these natural isomorphisms. Let's talk about, well, what happens if the set is a sum, what happens if it's a product, and then, well, the merge functions for sums and products, well, it's just going to be essentially apply the isomorphism, merge recursively in each component, and then apply the inverse isomorphism to patch back up. And this general pattern works for, I mean, we might need some factorial action and so on to, like, for scaffolding, but generally it's just like unpack, merge, pack. And then in the base case, like the integers, we're going to have some kind of efficient end merging using radix sort or whatever linear time merge algorithm for integers that we want to use. And efficiency-wise, well, so suppose that end merge actually does run in linear time, which again, radix sort and so on can do. Then merge as a whole runs in linear time. And moreover, the output is actually linear, can be represented using linear space because we're just using these symbolic tensor products, so we're not multiplying anything out. Even in the result, like in the final result, you might want to enumerate, but you can still do it in linear space because you're just streaming the tuples. Okay, so finally, let me show how this can be generalized to three-way joins. So bear with me if this is a little unreadable, but basically to write it compactly, we would just define this infix operator, which is just, well, it's more or less like functorial mapping. And then, well, suppose we have we want to merge three different tables and three different attributes. So think about like X has attribute 1 and 2, Y has 1 and 3, and Z has 2 and 3. Right, so it's kind of a cyclic three-way join. Well, what we do is just, well, merge in the first one, and then map over the result and merge in the second one, map over the result, merge in the third one, and then just combine the results into a triple. And I mean, the sort of the details to be fleshed out, but essentially this can be written down as a Haskell program that is about as long as this, like it's like 3 or 4 lines of combining higher order functions, and this is basically the algorithm that solves this problem in 4 seconds that took MySQL almost 2 hours. It's that simple. So if the input is size n, this runs in n square root n. In general, it's what is known as worst case optimal, which is so suppose that the 3 inputs have different sizes, and it's a bit more complicated to state like what is a good runtime, but there are definitions for this called worst case optimality, and this algorithm satisfies that. And also in practice, it runs quite fast. Right, so what did we do? Well, we developed linear algebra, module theory, but actually, we started out with linear algebra, then it became module theory, and actually now it's sort of turning into general additive categories. It's a very general framework, actually. But it turns out even in this general framework, we can do databases and query processing. We get like just using these natural isomorphisms and abstract ideas, we get efficient data representations, we get efficient join algorithms. And so, therefore, I submit to you linear algebra as a query processing language. Like it's a nice way to write down queries. I mean, I would say just at least as good as SQL for as far as it applies. We get things that are nice, functorial and natural. We get efficient symbolic representations, tensor products, scalar multiplications, and we get very efficient joins. And well, that's it.
I think we can't hear you, Max.
Okay. That better?
That's better.
There we go. Sorry about that. Thank you, Mikkel. So please continue asking questions on the Zulip. We have a few already. First, Ohad and a few people agree with this question. There was some confusion about the unary coproduct. That maybe it was a typo. Because you said,
Unary coproduct.
yes, that it was it supposed to be. It said the when you had the this page that the unary coproduct was the ring K, but should it be V?
Oh, right. Yeah. It should say V here.
Okay.
Yes.
Yeah. Okay. Great. And Manuel asks, how can one canonicalize the tensor product? There is usually no normal form, I believe.
Right. So yes. So if you have the tensor product over two like generic modules and you don't know anything about them, then you can't really compute the canonical form. You can only actually do it if you have knowledge that the modules are free modules, for instance. Which is kind of, well, that's like part of the point is that by taking this general approach, instead of saying that if you're doing linear algebra, for instance, you might say, well, insist that everything has a base, and then, well, that means that we can define the tensor product as only on free spaces, and do canonical canonicalization and so on. But yeah, it's actually an important point that we're defining the tensor product in general. With no assumption about the spaces, and therefore we don't want to do canonicalization, and we can't do it.
Yeah. Okay. So Kim Yo asks, you begin the talk with an impressive result where module theory trumps MySQL in the case of a triangle query. But what about the other way around? Are there cases where the module theory turns out worse than SQL? Or do you have some kind of result that the module theory always beats the relational algebra?
Interesting. So I don't think I have yet. I think I've yet to encounter any specific case where I was like, with module theory just simply can't solve. Because the thing is, you can always just, you can always just use the, like you're dealing with polysets, right? So you can always just deal with it using this mapping out principle, and just use like any function. I mean, you can plug in any function here, so it's kind of cheating a bit.
I think it's not an expressivity question, but more of a efficiency question.
Right. Well, but the thing is that, well, module theory in itself doesn't really have like a complexity.
Right.
I mean, it's kind of. So this particular, like, I mean, think of it as a theory, and the specific Haskell's limitation is like a model of the theory.
Mm-hmm.
So I mean, to me, it doesn't really make sense to say that this theory is faster than the other theory. It's more that I think it lends itself to more efficient implementations more naturally.
Mm-hmm.
At least that's my. I mean, I don't think we've kind of got to the bottom of it yet. So I mean, kind of the jury's still out on this, I think. But so far, I think it looks like we're winning out.
Okay. And then Sam Lindley had a question. Would you like to ask that?
Yeah, so that's really following on from Kimi's question. I started by asking, well, have you carried out an empirical evaluation? Then I realized, obviously, you have done some. I was wondering if you could tell us a bit more about that. And I'm really interested in there's a kind of follow-up from Pierre Marie as well. Should database implementers be using your theory as the basis for their engines rather than SQL? And do you have any evidence for that in terms of the actual and experimental results as well as the theoretical results?
So here's the thing that I think that the module theory is incredibly the category theory in particular is incredibly useful for like developing these concepts and like deriving these efficient data structures and algorithms. But the thing is that once you have derived them, you can kind of backport them to the old systems, right? So, I mean, so this join algorithm, you can implement it sort of, you can sort of lose the module theory and still implement, implement like the functionality of it to get efficient joins. So I think it's more akin to like how every object-oriented language is getting lambdas because they're sort of backporting functional programming features. Kind of the same thing, I think.
So I mean, do you have any plans to do that or to help database developers to do that, or are you just going to hope that they will see your work and steal it?
So we're trying to get published in a more sort of database-oriented place to actually sort of get more in contact with these people because, we haven't really had much success yet, like convincing actual database people that this is.
I mean, might I suggest that the way that you might convince them would be to build a larger scale experiment.
Right.
If they can see, look, I can actually run this on my real database I care about, and it makes it go much faster, then they'll listen.
I see Fritz has a comment. Fritz, do you want to unmute yourself and...
Yeah, I'm just complementing what Mikkel said. It's the case that during the study of so-called worst-case optimal query evaluation, that the classical approach, which is the system R approach, which has streams of records as the intermediate data structures, and query optimization you learn in database systems, is inherently, this is proved to be, so it's inherently incapable of expressing a solution that runs in less than quadratic time for triangle queries. In general, the class of queries, it's called cyclic queries, is very hard for database systems. They tend to have special rules or special code that they dispatch to because they're using flat records that corresponds to multiplying out the tensor product. While here it's being kept in a lazy data structure, and if you have a morphism, right? You have a tensor product of two things, you can just apply it. Computing cardinality is a simple case. So that's why I would argue that even if you take indexing into account, so which means, because that's not part of relational algebra. So as Mikkel said, there's relational algebra at the computational model. So let's add indexing in there. Those can be expressed as mentioned in asymptotically worst case linear time. So that would indicate that, at least asymptotically, the standard implementation techniques can be emulated in this fashion, at least, and in some cases beaten, because there's more data structures than just flat streams, lists of records.
Great.
Thanks.
And I may just ask, I've been in touch with a number of database people, and they basically, I completely agree with work on that, and we'll be working on that, but it's a very strange model to them. So the idea of having kind of other data types than that is not entirely new. There is so-called factorized databases, which are parts of, they basically have symbolic Cartesian products. But otherwise, most of the regime follows streams of flat records, so that if you have a Cartesian product or a join, it gets multiplied out into a huge intermediate stream of in the worst case, the Cartesian product becomes quadratically bigger than the input. In our case, it's just as big as the input, it's just a pair.
Great. That sounds very interesting. Let's keep this conversation going in the gather. The